In the last video, we introduced the concept of deprotonating the alpha position of an aldehyde or ketone in order to yield a deprotonated alpha position, which is stabilized by resonance and referred to as an enolate. In this video, what we are going to do is take this a step further and look at what types of reactions those enolates, those deprotonated alpha positions of aldehydes and ketones, can undergo by focusing on what's referred to as the Aldol reaction, or sometimes referred to alternatively as the Aldol condensation. When we break down this word, the term aldol, the ALD part refers to aldehyde, and technically this is more accurate to say aldehyde or ketone, but the word would get pretty convoluted if we tried to merge aldehyde and ketone into a single word there. So aldol refers to aldehyde or ketone. OL refers to alcohol. And so what an aldol reaction is going to yield is a product that has both an aldehyde or ketone functional group in it, as well as an alcohol functional group. And that's the origin of this term aldol. It's not someone's last name or anything like that, as is sometimes the case with these reactions, but instead it refers to the specific functional groups that we will find in the final product of these reactions. In this particular video, what we are going to do is introduce the mechanism for this reaction so we can see the nuts and bolts of how this reaction works. And we're also going to focus, as we do that, on intermolecular reactions. That refers to, when we say inter, it refers to two separate molecules coming together and reacting. In the next video, what we're going to focus on as one of our topics is intramolecular aldol reactions, where we'll have the two functional groups necessary for reaction present within the same molecule, and they react with one another within that same molecule, hence making it intra rather than inter. Inter is referring to like having two separate ethanol molecules that are coming together and reacting. So as we start into this, let's go ahead and take a look with no further ado at the mechanism for the aldol reaction. I'm going to do this mechanism for the aldol reaction by starting with, as our starting structure, two butanol molecules. So that is, of course, our 4-carbon aldehyde. We remember from our days of learning about aldehydes and ketones. We're going to react that with sodium hydroxide as our base. I'm using an equilibrium arrow here because acid-base reactions exist in equilibrium. And the aldehydes and ketones, the alpha positions, have a pKa value of around 17 or so they're not super strong acids, so you don't expect them to be fully deprotonated, but instead there to be an equilibrium that exists here. So in this mechanism, anytime we have a relatively strong acid or strong base present in a reaction mixture, the first step is going to be either protonation if we have an acid present, or deprotonation if we have a base present. So we have a base present here, so we want to, in the first step of the mechanism, deprotonate. So I'm going to draw out my butanol molecule. So here I have my 4-carbon butanol. I'm going to explicitly show the two hydrogens here at the alpha position, because as we learned in the last video, in aldehydes and ketones, those are going to be the most acidic position of the molecule. And so we'll bring in then our base, sodium hydroxide. You don't really need to write out the sodium there. It's going to be a spectator, meaning it's along for the ride, but it's not actually doing anything in the reaction. So my equilibrium arrow here of this acid-base reaction. And I have my base come in and grab a proton from that alpha position of the acid. So we're going to remove a proton from the most acidic alpha position, and that only alpha position in this molecule is the one right here. So that's where we're going to remove that proton. As we remove the proton there, we also have to break this carbon-hydrogen bond right here and move those electrons onto that alpha carbon. So therefore, our product of this reaction is going to look like this. We will still have one of the two hydrogens there at the alpha position, so I'll go ahead and show that. You don't necessarily have to show that. It's implied that it is there. As long as you have the negative formal charge in place, you can infer that that proton still has to be there and that the other one was removed. Our other product of this reaction, if we want to be really complete here, is that our base, which I'll write out specifically as the hydroxide anion, formed a bond to hydrogen, and therefore it is now H2O as our conjugate acid product, because our base, hydroxy, picked up a proton. Once the base picks up a proton, it becomes the conjugate acid. So our conjugate base product, our enolate right here, we can draw a second resonance structure for to illustrate that this is a relatively stabilized intermediate. By taking the lone pair electrons, bring those down to make a carbon-carbon double bond, bring the pi bond up onto the oxygen, and that will give us this structure. So double bond there, single bond to the oxygen, which is going to be an oxygen anion because 3 sets of lone pair electrons. Plug in my hydrogen there so that I don't accidentally add an extra carbon in the structure. And the hydrogen here that I showed in red in the original resonance structure, that's optional. We could leave that out if we want here. So now that we have done this, I will go ahead and label, for those keeping track at home, that this first step is what we would classify as a deprotonation step, because we've removed a proton from that alpha position in this acid-base reaction. So now that we have done that, we've created this resonance stabilized enolate intermediate. And since one of those 2 resonance structures has a negatively charged carbon in it, that carbon can act as a nucleophile. And that is super valuable because carbon nucleophiles are very useful for forming new carbon-carbon bonds. We learned that back when we were looking at Grignard reactions. We created a Grignard reagent where we could think of that carbon in the Grignard reagent as acting as a carb anion, and it was able to perform as a nucleophile to react with electrophilic carbons and hence create new carbon-carbon bonds. And that is exactly what's going to happen here. So let's go into step 2 of the mechanism. I'm going to take that carb anion as the resonance structure that I will continue on with here. I'm going to put in the lone pair of electrons, and I am going to omit the red hydrogen atom that we had here. It's not essential that it be there. It's implied that it's there as long as we have that negative charge, and I'm using the lone pair electrons here so that I can show what's happening in the mechanism really clearly. So in our reaction mixture, we started with exclusively butanol and base. That is what we have available. So in this reaction, in our mixture that contains this enolate intermediate, remember that the acid-base reaction is in equilibrium, meaning there's also some of this unreacted butanol present as well. And so what happens here in the second step of the mechanism is that the deprotonated butanol is going to find another molecule in the container that still has its alpha proton. And so what we will do here is come in, and the carbon at this alpha position acts as a nucleophile. Nucleophiles, as we have learned, are very eager to come in and form bonds to carbonyls, and that's exactly what it's going to do. It acts as a nucleophile to form a bond to this electrophilic carbonyl carbon. We've seen time and time again that those carbonyl carbons are very positively polarized and hence nicely electrophilic. So we've made a new carbon-carbon bond here using the electron pushing arrow that we showed in blue. And as we do that, we also have to take the pi electrons from the carbonyl group, move those up onto the oxygen so that we don't ever go over the octet rule. And so I will draw out the product that results from this. I'm drawing out my structure that corresponded to the enolate, and I'm going to highlight that in yellow here on my starting structure. And I'm going to highlight those same atoms in my product there. And then at the alpha position of our starting structure, which corresponds to here where I've listed alpha in blue on the starting side, blue on the product side, that was where we created a new carbon-carbon bond. So I'm going to make a new carbon-carbon bond in blue here. And that new carbon-carbon bond needs to connect over to a carbon of what was the carbonyl, single bonded to oxygen, single bonded to hydrogen, then bonded to this 3-carbon chain here. So let's go ahead and draw that out. So our carbon that we've just formed a bond to has a hydrogen directly linked to it. It has an oxygen, which is going to be an oxygen anion, so there's 3 sets of lone pair electrons. And we will also have a 3-carbon chain here, 1, 2, 3. And so I will go ahead and highlight to illustrate where all these atoms came from. So we had our 3 carbon chain plus the carbonyl, so 3 carbon chain plus what was the carbonyl. The carbonyl had linked over to the nucleophile, so that's why we have the blue bond here. And then what was that carbonyl to start with? It still has a hydrogen bonded to it, still has an oxygen bonded to it, so I'm going to highlight those in red on the starting side, red on the product side as well. And so as a consequence or outcome of this reaction, we've made a new carbon-carbon bond right here. So making that new carbon-carbon bond right here, we have taken 2 relatively simple starting materials and we have essentially doubled the size of these. We've gone from 4 carbons in our starting materials to 8 carbons in the product, making this a really useful reaction for taking simple starting materials and quickly building up complexity of them, making this reaction super duper useful. So now that we've done that, what's going to happen next? So thinking about what happens next, we will go on, and I will list out here that step 2, just to dot all our I's and cross all our T's, is where the nucleophilic enolate, specifically the nucleophilic enolate carbon, attacked the electrophilic carbonyl to make a new carbon-carbon bond. As a result of that step, we can now take that structure that we've just made as a product of that reaction, and we can bring that on down into the next step here. And I will go ahead and draw out that structure. I'm just redrawing the structure that we have as the product of the last step. And now looking at this structure that we have just created, what we will see is that we are very close to a final product that would have no formal charges if only we protonated this oxygen. And looking around, we have a source of proton available. Indeed we do, because we have water present in the reaction mixture. And often these reactions are run not only in sodium hydroxide, but there will also be water there as well. We've also created water of our own here as a result of the first step of the reaction mechanism back at the beginning. So what we can do then is bring in your water. Oxygen anion comes in, grabs that proton from the water, force the OH bond to break. That's going to give us OH anion as a product of this step, as well as our product of this reaction. So let's go ahead and draw out the product, which is going to look like the reactant, except that we have protonated the oxygen anion here. So it became OH. So as a consequence of this reaction, going back to that theme about aldol, where the ALD referred to aldehyde or ketone, and the OL referred to an alcohol, we have done just that here. We have created a product that has both an aldehyde or ketone group, highlighted in red, and we have also introduced an alcohol group into that same molecule, allowing this to be referred to as our aldol reaction. Now, this is a really great way. If you notice, in this reaction product, we have 2 functional groups that are separated by just this single carbon here, the alpha position carbon. And so if you're looking at a structure and you're analyzing and trying to decide how you might synthesize, and you see that there is a functional group here, then there's your alpha position, and then another functional group, aldol reaction could very well be a useful way to go about doing that, because we could take this aldol product that we've created here and do a variety of things. Like we could reduce this carbonyl group to make this a dialcohol, a diol. We could also do things like oxidize this to create a carbonyl group here and a carboxylic acid group here. So there's a bunch of different ways that we could go from here now that we've created this new carbon-carbon bond, because not only have we created a new carbon-carbon bond, but we've also created a molecule that has 2 different functional groups that we know of a variety of ways to react, because we know all sorts of alcohol reactions and we know all sorts of aldehyde and ketone reactions at this point. So this reaction can be really clutch for going forward with making complex products out of relatively simple starting materials. But there's more, because when we are looking at these structures that have an aldehyde group or ketone group, and it is beta at the beta position, a hydroxy group, we can actually readily undertake a dehydration reaction of those molecules. And when we do a dehydration means loss of water, and we do that by heating in either acid or base, and by heating it up, that will allow us to remove or dehydrate this hydroxy group and replace it with a carbon-carbon double bond there. So let's go ahead and do that for this so-called beta hydroxy aldehyde or ketone that we have created here. So we're going to go ahead here and we're going to look at dehydration of aldol products. So the aldol reaction itself initially is going to yield a beta hydroxy aldehyde or ketone. And then what we can do from there is, if the reaction is run with substantial heat, the heat will give the energy required for a dehydration reaction to occur. So if you want to take the aldol reaction and dehydrate that beta hydroxy aldehyde or ketone product that we created to remove the hydroxy group and replace it with an alkene group, all you need to do is fire it up. Add some heat to the reaction mixture. And what do we mean when we say add some heat to the reaction mixture? Because you could be thinking everyone's definition of hot is a little different. Generally speaking, 100 degrees Celsius or more is adequate for this type of reaction to take place. So let's take that product that we created by doing an aldol reaction with 2 units of butanol and imagine that we had heated it up to 100 degrees Celsius. The reaction wasn't run on ice or it wasn't run at room temp, but it was run at 100 degrees Celsius. What's going to happen there? So what would happen there up until this point is that we would create that same aldol product that we were just looking at. So I'm just redrawing the aldol product that we had already created. We have our alcohol group beta to the... That's one way to know you've done these reactions the correct way, is that you should always end up with the hydroxy group beta relative to the carbonyl group of the aldehyde or ketone. So this was our original aldol product. And this is what would persist if we were running the reaction at low temperature. On the other hand, if we were running the reaction with heat at, say, 100 degrees Celsius, which we could recognize in a reaction because it would have to be labeled that the temperature was 100 degrees, we'll say, there's base floating around in solution because we used our base there as a catalyst. And so what would happen here in this reaction is that with the base as the catalyst, it's going to come in and in an acid-base reaction, it would remove the proton at the alpha position because remember that proton is relatively acidic. We saw that before. It's still alpha to a carbonyl group in this structure, so it's still acidic. So that proton is going to be lost. That would break this carbon-hydrogen bond. The place for it to go is to come down to here to make a carbon-carbon double bond. In order for that to happen, something's got to give here. At the bonds, we have our carbon-hydrogen bond, carbon-carbon bond, and carbon-oxygen bond. This carbon-hydrogen bond doesn't want to break because if it did, the electrons would have to go onto the hydrogen. That's not going to be very favorable because hydrogen is not very electronegative. But on the other hand, if we break this bond and take those electrons onto the oxygen, oxygen is relatively electronegative, and so it's going to be pretty okay with taking those electrons. So we would generate as a result of this hydroxide anion, demonstrating how the base acts as a catalyst of this reaction because we're using it up here, but we are also reforming it in the reaction. The organic product of this reaction is going to have our carbonyl group still in place, hydrogen of that aldehyde group, 4-carbon chain there, and then our carbon-carbon bond right here will have become a carbon-carbon double bond. drawing out the rest of the structure here. We could omit that hydrogen if we wanted. It's implied that it's there, but I'm going to go and draw it anyway. And our 4-carbon chain there. So we have, as a result of this, to recap, when we heat this up, that's going to provide the energy for overcoming the activation energy, allowing the base to grab that proton from the alpha position of the acid. The electrons from breaking that bond are going to come down to make a carbon-carbon double bond as the oxygen leaving group pops off there to give us, ultimately, a carbon-carbon double bond. And this product, going back to chapter 15 or so, we refer to as a conjugated product, because remember that conjugation refers to structures that have a continuous sp2 system as a result of having this pattern of double bond, single bond, double bond. So a conjugated region of the molecule is what I have highlighted in yellow in our structure here. We have a continuous sp2, 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 sp2 system, alternating single bonds and double bonds, and that actually creates a lot of stability within this molecule. And so once we get to here, the reaction is not reversible because this is very, very low energy, and hence the reaction can't go backwards at this point. That's why I've not shown this as a reversible arrow, is we can't go backwards because of the fact that this conjugated structure is particularly stable. This is not an equilibrium process, unlike the other reactions that we looked at to get up to this point where we're doing a bunch of acid-base reactions and things of that sort that would be reversible. So as we wrap this particular video up, we are going to, in the next video, go into additional examples of various types of aldol reactions, focusing on reactions where we have two aldehyde or ketone groups within the same molecule that will allow us to do an intramolecular reaction where we can react one of the deprotonated beta positions with the other carbonyl group that's in the molecule. We'll also look at what we refer to as crossed aldol reactions, which are where we are using two different aldehydes or ketones and reacting those with one another, in contrast to what we learned here, which was where we were reacting two identical aldehydes or ketones with one another. And so the next video will continue onward, looking a bit deeper at these aldol reactions.